Hello, am I audible? Hello, hello, am I audible? Okay, so this is the third live problem solving session for the course Physics to Computational Thinking. So here I'm going to discuss about the Euler's method and Ranjit-Gupta method, and then show some codes in Mathematica. So these methods are basically used to solve the ordinary differential equation, where we assume that the fxy is y dash or dy dx. Then the first method is Euler method, second is modified Euler method, and third is Ranjit-Gupta. So we'll start with the normal Euler method, the basic Euler method, where we use y2 equal to y1 y1 equal to y0 plus h f x0 y0. y2 equal to y1 plus h f x1 y1 dot dot, then yn plus 1 yn plus 1 is equal to yn plus hf xn yn. So this is the process of the basic Euler's method. Now I will show one very basic example. Now here the problem is y dash equal to minus y with condition y0 equal to 1. Now here clearly we can take the value of h equal to 0.01, and then here f of xy equal to minus y. So now we will start with, so basically the initial condition is y of 0 equal to y equal to 1 at x equal to 0. So here we can find the value of y at x equal to 0 0.01, 0 0.02, 0 0.03 and so on. So y at 0 0.01 equal to y naught plus h f of x naught y naught, which will be, the y naught is given by this particular value, so it is 1 plus h is 0.01 then f of x naught y naught. So here x naught is 0, y naught is 1. So basically f of x naught y naught equal to minus y naught equal to minus 1. So it will be minus 1, so it will give 0.99. Then again y at 0.02, so it will be y1 plus h f x1 y1 equal to so here y1 is 0.99 plus 0.01, then f of x1 y1 is minus y1, which is minus 0.99. Then for y at this, so for example I can write down that this is the x1, this is x2, this is the x3. So this one will be y2 plus h f of x2 y2, so 0.9801 plus 0.01 multiplied with minus 0.9801, which gives 0.9703. Then y equal to 0.04 y3 plus hf x3 y3 0.9703 plus 1 minus 0.9703, which gives 0.9606. So basically we get a table of x and y. This 1.99, 0.9801, 0.9703, 0.9606. So this is the way to use the Euler method. So now here we can also change this value 0.01 to 0.005 or something, and then we can use, and then we can find the value of y from this particular differential equation at if we use h equal to 0.005, then we can find 0, 0.005, 0.01, 0.015, and so on. Now there is another method, that is modified Euler's method. Where the formula is used y1 n plus 1 equal to y naught plus h by 2 f x naught y naught plus f x1 y1 n. 0 where y10 can be determined by using this formula hf x naught y naught. So this one is the basic Euler method, but this is the modified. Now we can see an example. Determine the value of y when x equal to 0.1, given that y0 equal to 1 and y dash equal to x square plus y. Now here x equal to 0.1, so we can take h equal to 0.05. H equal to 0.05, x not equal to 1, sorry, x not equal to 0, y not equal to 1.0. So f of x naught y naught equal to x naught square plus y naught, which gives 1.0. Hence y10 equal to 1.0 plus 0.05 multiplied by 1.0, which gives 1.05. Now we have x1 equal to 0.05 and f of x1 y1 0 equal to x1 square plus y 1 0. So x1 square is 0.05 whole square plus y1 0 1.05, which gives 1.0525. So now f of x 0 y 0 plus f of x1 y1 0 by 2 is 1.0262. So this average of f x0 y0 and f x1 y1 0 is taken because of this part, this particular part, that is h by 2 f x0 y0 plus f x1 y1 p power n. So this average is 1 0. So now y1 1, that is 1, y naught h by 2 fx0 y0 plus f of x1 y1 0. This is 1.0513. Now repeating the same procedure, we can find that y1 2 will be 1.0513. Hence we can take y1 as 1.0513. Okay, so basically the y11 is 1.0513, then y12 is 1.0513, so we can say that the value of y1 is not changing, so we can easily conclude that the value of y1 is 1.0513. Now again we will repeat the procedure with x1 equal to 0.05, y1 equal to 1.0513, and h equal to 0.05. And then we can repeat this whole procedure from starting from this particular line, and we will obtain the value of y2. Y2 means the value of y at x equal to 0.1. So there, when we start with the same procedure, so we will find first the y2 0. So y2 0 will get, I'll just write down the values, 1.1040. Then the first order y2 is 1.1055. Then the y2 is 1.1055. Hence we put that y value of y at x equal to 0.1 is 1.1055. So this is the process to solve the differential equation and obtain the value of y using modified Euler's method. Any question? Okay, so if you guys have no question, then I will proceed to the Ranjikutta method. In short, it is also called the RK method. So this method has many types, so we'll just mention the second order and the fourth order Ranjikutta method here. For second order, the y1 is obtained using y0 plus y0 plus half k1 plus k2, where k1 is h f x naught y naught and k2 is h f x naught plus half h y naught plus half k1. H f x naught plus half h and y naught plus half k1. And there is another Ranji-Gupta method, that is the fourth order, where the y1 is obtained using y0 plus y by 6 k1 plus 2k2 plus 2k3 plus k4, where k1 equal to h f x naught y naught naught, k2 equal to h f x naught half h, sorry, this one will be x naught plus h and y naught plus k1, there will be no half. X naught plus h and y naught plus k1. Now this one is y naught plus half k1 and k2 is k2 k3. K3 is h f x naught plus half h y naught plus half k2, k4 equal to h f x naught plus h y naught plus k3. So these are the values for k1, k2, k3 and k4. So now we'll look on a very basic example. So here the problem is given dy dx equal to y minus x, where y0 equal to 2, find y1 to 1 and y2. Correct to 4 decimal. So now first we will go with the second order Ranji-Gupta method. second order Ranjagupta method with taking the value of h equal to 0.1. So now using the value of h equal to 0.1 we'll get k1 equal to, okay, so first of all the uh, f of xy equal to y minus x. Now considering the value h equal to 0.1 we get the value of k1 equal to 0.1 into 2 minus 0, that gives 0.2. And similarly the value of k2 equal to h f x naught plus h y naught plus k1. So h f x naught plus h y naught plus k1, 0.1 if y naught plus k1, 2 plus k1, 0.2 minus x naught plus h, that will give 0.2, 0.21. So y1 y at 0.1 gives us 2 plus half 0.2 plus 0.21, so 2 plus half 0.41 equal to 2.2050. Now again if we proceed further, like we want to obtain the value of y2, that is y at 0.2, then we'll assume the value of x naught equal to 0.1 and y naught equal to 2.2050, which we obtained from here. Now hence k1 will be 0.1 multiplied by 2.105 equal to 0.2105, and k2 will be 0.1 2.4155 minus 0.2 equal to 0.22155. So we get y2 equal to 2.2050 plus half y2 equal to 2.2050 plus half of 0.2105 plus 0.22155, which gives us the value 2.4210. Again proceeding similar way, we obtain y3 y.3 2.6492 and y4 y at 0.4 equal to 2.8909. This is the way we use the Ranjagupta second order. Now again we can change the value of h equal to here we have used the value h equal to 0.1. Now we can change the value of h to 0.2. So here if we use the value h equal to 0.2 and try to compute the value of y of 0.2 and y of 0.4, then we have the values h equal to 0.2, x not equal to 0, y not equal to 2. So k1 equal to 0.4, k2 equal to 0.44. So y of 0.2 will be 2.4200 and y of 0.4 will be 2.8880. Now the differential equation was given as dy dx equal to y minus x, which gives us the exact analytical solution 1 y equal to x plus 1 plus e to the power x. The exact value of y2 equal to 2.4214 and y of 0.4 is 2.8918. So here we can actually make a table and compare the values. X computed, x exact, y difference. So now this is 0.2, at h equal to 0.1 we get the value 2.4210, h equal to 0.2 we get the value 2.4200, exact is 2.4214. So the difference is 0.004, and here the difference is 0.0014. Again for 0.4, when we take the value of h as 0.1 we get the answer as 8909, and when we assume the value of h as 0.2 we get the value 2.8880, but the exact value of the y at x equal to 0.4 is 2.8918. So here the difference is 0.0009 and 0.003. So here you can see the smaller the better the accuracy is. Basically the difference is decreasing. So if we take h equal to 0.05 then the accuracy will increase further. Now we will see the Ranjit-Gupta fourth order. Ranjit-Gupta fourth order. So here to determine y equal to 0.1 we have x naught equal to 0, y naught equal to 2 as usual, and h equal to 0.1. Now we will find the value of k1, k2, K3, K4. So I'll just write the value. K1 equal to 0.2, K2 equal to 0.205, K3 equal to 0.20525, and K4 equal to 0.21053. Hence, we'll use the formula for the fourth order, that is this formula: y naught equal to 1 by 6 K1 plus 2K2 plus 2KT plus 2K4. Q1 plus 2K2 plus 2K3 plus K4, which gives 2.2052. Similarly, y of 0.2, we get 2.4214. So this is an example for Ranjagupta second and fourth order. So now here we can again the third example. We will again see another example of Ranjagupta method, that is given dy dx equal to 1 plus y square, where y equal to 0 when x equal to 0, find y.2, y.4 and y.6. So here we take h equal to 0.2 and h equal to 0.2, x naught equal to y naught equal to 0. So now we obtain k1 equal to 0.2, k2 equal to 0.2.1 1.01, that is 0.202, k3 equal to 0.21 plus 0.010201, 0.20204, k4 equal to 0.21 plus 0.040820, 0.20816. So now the value of y at 0.2 will be 0 plus 1 by 6 k1 plus 2k2 plus 2k3 plus k4 equal to 0.2027. To compute y 0.4, we take x naught equal to 0.2, y naught equal to 0.2027, and h equal to 0.2, which gives us the value of k1 equal to 0.2, 1 plus 1 plus 0.2027 whole square, that is 0.2082, k2 0.2, 1 plus 0.3068 whole square equal to 0.2188, k3 0.2, 1 plus 0.3121 whole square is 0.2195, k4 equal to 0.2, 1 plus 0.422 square equal to 0.2356. So these are the value of k1, k2, k3 and k4 for the fourth order Ranjagupta method. Now we can finally calculate the value of y at x equal to 0.4, that is 0.2027 plus 0.2201, which is 0.4228. Now again, if we proceed with the same, like taking as x naught equal to 0.4, y naught equal to 0.4228, h equal to 0.2, then we'll obtain y equal to at y of 0.6 as 0.6841. Now again I will show just another example of this three methods I have shown here: Euler, modified Euler and fourth order Danjigupta. So any question till now?
No, sir.
Okay.
Sir, will you be sharing video link for this? I miss 10-15 minutes of first
Yeah, I mean
session.
I am continuously sharing the video links. I mean I'm sending the NPTEL, so you should get that. Did you get the last 2 weeks video?
No, no, not from NPTEL, sir. Last time you only shared one of your video link.
Okay, that's weird, but okay, then okay, I will actually contact them and ask them to share. Okay. uh, so now there is another example, but here it is not exactly example, it is just a comparison between the not between it is the comparison among the process I have uh, mentioned here, that is the Euler, modified Euler and fourth order Ranjagupta. So here we will consider initial value problem, that is y dash equal to 3x plus y by 2. This is the differential equation with y naught equal to 1. So the exact value of y at point 2 is 1.16 1.16722.193. Now here I will show a table method value of h computed value Euler uh, okay method h computed. Now Euler value is 0.2, computed value is 1.1000000. Then h is 0.1, the computed value is 1.132500000. Then for h equal to 0.05, 1.1495758. Then modified Euler is 0.2, 0.1 and 0.05. Here for 0.2 the value is 0.00000, 1.1500000, 1.162862242, and here the fourth order RK method. Again the value of h are same, 0.2, 0.1 and 0.05. Now 1.167220083, 1.167222186, 1.167222193, and as I have mentioned, the exact value is 1.167222193. So here you can see that the Euler method, this one is the slowest method. Then the modified Euler, which is actually by changing the value of h, the smaller the value of h, the accuracy is getting higher. So here when we use the value of 0.05, we get 1.162862242. So modified Euler is at least getting to the 1.16. And the fourth order Ranjit-Gupta method, when we use 0.2, I mean this is the 4 times higher. When we use the value of h as 0.2, we get 1.16722, and when we use 0.05 we will get the exact value. So we can finally conclude that the fourth order Ranjit-Gupta method gives the accurate value for h equal to 0.05. So this is the comparison between these three methods, and as we can see, the Euler normal basic Euler method is the slowest, and the fourth order Ranjit-Gupta method is the fastest to converge at the correct value for solving ordinary differential equation. Okay, so now I will stop sharing, and then I will just share the Mathematica, where I will just show some codes. Now is my screen visible?
Yes, sir.
Okay, so I'll go to the full from cloud. So here I will just show some codes which is related to or kind of similar to the codes shown in the lectures and in the assignments. So basically this is a function. So this is the way you can take a derivative of the function and then also use the integral. Also there are a lot of things that you can do here. The first one is like the plot. So for example, if we
Excuse me, sir.
yes
Sir, can you please show that how to type that dx of x3? I was
uh,
trying with the colon for omega, and it was not taking for omega. So I was using W sign there earlier.
oh okay. This can you type this three dots thing in your Mathematica?
Oh, I was typing colon. How to get this three dots?
Okay, just let me check that it
Three
is
dot.
working
It's
here first. Del yeah. So these three dots come from the escape button. Did you check?
okay. Only escape.
Yes. First you have to
No
type the
control,
escape
etc.
button. Then you have to type like
Okay.
something omega or something. Or here you also use you can use that W. And then again you have to use the escape button.
Okay. And so can you add something like if we have two values, one in numerator and denominator, so how can we bring that boxes wherein
Okay.
we can
So for
type
that
numerator?
boxes, yeah. Uh, okay. Let me show you in this way. Let's write a function. Mm, now something you have written like x. Okay. Now what you have to do, you have to mm, this happen in the desktop version of the Mathematica, but here it is not working exactly. But no, this one. I have checked that in the Mathematica desktop version and it is working fine there. Uh, Actions work. Okay, let me just yes. Can you see the my desktop? I mean the desktop version of Mathematica.
Yes, sir.
Yes, so here like I have written the same thing in the Wolfram count, that is the g x underscore equal to x by. So here I typed x. Okay, after that I type control slash, and it automatically taking that fraction thing. But in Wolfram count it is not taking. I don't know what is the reason. Okay, so in
Okay, sir. Okay.
desktop version you have to do in this way.
But that desktop version will be paid, na, sir? Paid
Uh,
version, na?
yeah, you can have paid, and there is also a other way to get that version. I mean Mathematica.
Okay, okay, okay.
But in Wolfram Cowl this should also work, but I don't know why it is not working. This, don't know why it is not working anyway. So now this is the function I have written, gx equal to x by x square minus 2x plus 3. So I will just plot it and we will get this thing. Now we can do a lot of things like full simplify and all those things. Here the options are available, like finding the maximum, global minimum, and all those things are available in here. Now what we will do, we'll just use same function like g of 2, it is 2 by 3. Now I will assign is equal to 2 to 3, it is 3. So we are just using this particular command to modify the value of this particular function. Now again we can do like g of uh, so this is the s by 3 minus 2s plus s square. Now this is how you define a function. Now get back to the solution of ordinary differential equation. So I will just show the solution for the equation I have used here. I mean used to show the example of Euler and modified Euler and Ranji-Gupta method. So first one is y dash of x equal to minus y of x with the initial value y dash, sorry, y of 0 equal to 1, y of x, this is the value e to the power minus x. Now in the first example I have solved it for 0.04 and obtained the value as y of 0.04 as 0.9606. Now exponential minus 0.04, it gives 0.960789. So this is the exact value of the exact solution, and that I shown in the first example was the solution obtained numerically. Again another I have shown solve. This one is for the modified of Euler's method, that is solve y dash x equal to x square plus y comma y of 0 equal to 1 x. This is the function yx minus 2 plus 3 e to the power x, like this. Now I have copied that and then I'll just put it like uh, I don't know what is the problem of Wolfram curve. So this is the function I have assigned it to gx. Now I'll just compute the value of the function at x equal to 0.1. So g of 0.1 is 1.10551. So what we have found here is by using the modified Euler is 1.1055, which is correct up to the fourth decimal place. And as you can if you can remember that during that calculation it was not changing its value after repeated iteration in the modified Euler method. We can plot this function and see that this is a this kind of function actually. Now in the last example where I have shown a table and compared the values obtained from Euler method, modified Euler method and Ranji-Gupta method. So in that problem it was solution equal to d solve uh, y dash x equal to 3x plus y by y of x by 0 equal to 1 y of x y. So this is the exact analytical solution of that particular ODE. Okay, now I will go to a I will show another solution, that is d solve y dash t plus 2y t equal to 3 exponential t. Yt t. Okay, so can anyone point out what is missing here? Okay, so the thing is missing is that I have written down the differential equation, but I have not mentioned any initial value like what is the value of y at 0 equal value of y at t equal to 0. So if I solve this one, it will be e to the t plus e to the minus 2t c1. Now I can change some values here and there, like okay, now this is the solution for this particular equation, but here what we can see is that there is a constant c1. So this is a parameter, like this is the general solution of this particular uh, equation. Now if we copy this and then just put some initial value like y of 0 equal to 2, you can see that we are getting a different, not so different, but we are getting some value of c1. Now again copy this and put, we get this value. Okay, so for different initial value problem we have got a different solution of yt. So now we will plot all the equation here. So basically manipulate plot exponential of t plus exponential of minus 4t multiplied by a comma 1 comma 2 comma, the range will be t minus 2 to 2 comma lot range all lot legends automatic comma a comma minus 5 to 5. So here you can see that the blue line corresponds to this general solution, and the second thing is the yellow line, that is corresponds to the value when a is 1 and it is 2. So this is basically the thing is that we are just showing the general solution and the particular solution of a equation. Now what happens if we put this one? This gives a value but at a very different location, because it is, I mean, the value of a is very different for here, but it is also showing the same family of equation. Yeah, so if I decrease the value of minus a, so I think I can reach that value. Yes, but here we can actually match the value of these two equations. We can show some solution for this differential equation, because for harmonic oscillator and harmonic oscillator and all those things, the this dissolve is very important right now. uh, y dash t minus 2 yt 4 cos t minus 8 sin t yt. Aha. So this is the solution for this particular equation. Again, minus 4x plus 3 minus 6 star exponential of x comma y at 0 equal to 0, sorry 8, y of x. So this is the solution for this particular differential equation. So now let's go into a little bit of physics. For example, if let's assign the value g equal to 9.8 and uh, v is 0 equal to 10, So basically some particle with a velocity, initial velocity 10 is going upwards, like you can think of throwing stone upwards or throwing something upwards, upward direction. So the uh, acceleration due to gravity is working downwards, so uh, it is basically trying to stop that particle from the motion, and the velocity is upward, so it is positive, but the acceleration due to gravity is in the downward direction, so it will be negative in the equation of motion. So I will just write it down. uh, Solve v vt equal to minus g comma p of 0 equal to v0 comma vt comma t. So this is the equation of motion for velocity, that is 10 minus 9.8 t. Now again we can use this particular thing to solve, like let's do some assumption here. T solve oh, okay, I have that example later, so I'll just stop here, and then I'll show the use of desolve value, that is this one. Desolve value y dash x plus y x equal to a sine x y 0 0 y x. This is the solution of this particular equation. Now what we will do, we will plot table sol of x a I comma I comma 7 x comma minus 2 to 10. This is the plot for the different value of I. Again, from this particular solution, that is the sol 6, if we need to find the velocity at different time, then we can use the table function sol 6 t 0 to 10. Now here it is showing that at 0 it is 10, which is same as the initial value, that is v naught equal to 10. Now after that at v equal to 1, that is 0.2, then v equal to 2 minus 0.96, and so on. Now again we will use the desolve. Now s of t, so here we are going to solve for the displacement, where the velocity or the first derivative of displacement is equal to minus 0.98, which is g actually, plus 10. So this is basically the same equation here, 10 minus 9.8 t. Now s of 0 equal to 3, s of t. So this is the equation for st, that is 3 plus 10t plus minus 4.9 t square. So if we can see that the problem was that if we have thrown something upward in the direction with the initial velocity 10 meter per second, you can say, or and then the acceleration due to gravity is 9.8 meter per second square downward. So the equation of motion is basically the acceleration v dash t equal to minus g, with the initial value v naught equal to v naught equal to 10. Then we solve that and get the equation 10 minus 9.8 t, and then we again solve the velocity equation and get the displacement, that is 3 plus 10 t minus 4.9 t square. Now we can change it and get a different value. Now again we can do the same thing with the displacement, that is we can create a table. So 7 t po 10. So here you can see that the initially the position was s equal to 3, then s1 is 8.1 and s2 is 3.4, s3 is minus 11.1. so you can say that the first the ball is going upward, then it is going downward, or something like that. Then this negative value for s is like meaningless here. Also it depends on the problem you are solving and where it we have started throwing the stone or ball, that depends. So you cannot, I mean, you can discard this value as it is negative, but it also depends on the problem what kind of value you expect from the solution. Again we get back to the same function, that is a desolve. Desolve y dash x 7 star this is a little complicated differential equation, that is like y dash equal to 7 y square plus x cube. Okay, now y x x, so we get the solution as 4 by 7 minus 4 by 7 x to the power 4 plus 4 c1, which is a constant.
Excuse me, sir.
Yes.
So that y of x raised to 2 into x raised to 3 we have mentioned, right? So is it taking separately that x raised to 3 is getting multiplied to the y square, or there is a need of bracket over there?
Okay, we can check that.
Oh, yeah, solution if changes then.
Yeah, it's not changing.
Okay.
Actually in it's these things like this yx to the power 2 and x to the power 3, this all things should go in the superscript, but why I don't know why it is not working here. I mean, I have tried all this example in the desktop version and it
Yes,
worked very well.
I was also trying. Yes, it is not taking in web version, sir.
Yeah, I am not sure why it is happening, but anyway. Fine. This is another equation that is solved, so now I will just plot it. Plot x t solve t. Oh, so this is the plot of this particular function e to the power minus 1 plus cos t. Now I will just go to the oscillator problem. Solve t solve x double dash t plus beta x dash t plus uh, omega square omega square x t equal to 0. Now x t comma t. So this is the general equation of the oscillator, damped oscillator, not forced oscillator. And now wait a second. X double dash t plus beta x dash t plus omega square. Oh, so this is the solution for the damped oscillator, that is exponential to the power this c1 plus exponential to the power this. Now there is another kind of desolve, that is the n desolve. So what it is going to do, the desolve is actually solving the differential equation and giving us a analytical solution like that is a has a some kind of form. But what NDSolve is doing, it will solve the problem analytic numerically. So like I have shown you the process of Euler, modified Euler and Ranjit-Gupta. So it is going to use some kind of process which is a more accurate process, rather mostly Ranjit-Gupta, but more accurate or higher order Ranjit-Gupta, so that it will give you mostly the this computing language uses the Ranjit-Gupta, but it depends on which language we are doing the problem. So yx cos x plus y x. So as you can see, this is not a very straightforward example, because it is like y dash x equal to yx cos of x plus yx. So this yx is already inside the cos. So solving this analytically may be troublesome. Now y 0 equal to 1 comma y x 0 30. So it has solved it with showing that the domain is 0 to 30. Now I will just let's see if it can. Yeah, it has solved it, but it is a very weird kind of solution. Now lot evaluate y x is uh, x minus 30 to 30 lot range, or what happened, lot called is 1 or 2
Dot again. We got dot there, sir.
oh
Before that, yeah.
Thank you. Yeah, so this is the solution, minus 30 to 30. Now if I change the range like 0, you can check the, you can see the plot. Also here if we change this, so basically in this particular line, the this x0 this x030 is actually saying this NDSolve to solve this particular OD differential equation in this range 0 to 30, and this one is for the plot. Okay.
Sir,
Yes.
is there any method like here we are getting a plot of this given differential equation?
Yes.
Can we have a kind of table of different values of on increasing the y values, like y is increasing, then how that differential equation is giving out its different values,
I mean,
or what with yes.
you are talking about y as a dependent variable or independent variable?
Uh, Here it is dependent, right, for
Y
y of
is
x.
yes, dependent variable.
So it depends on x, right? So we are taking x value from 0 to 30.
Hmm.
So these values, sir, 0 to 30, for
Hmm.
these all these values, can we have a different set of values? Here directly we are getting plot, but picking out that values is somewhat difficult here. Do we have any kind of function here?
Oh, you are talking about like if we get a value for like y at 0 and y at 1, and like you are asking me to
That
produce a
way,
table.
that way table form can be.
I think that should be done by this one. Let me check. This evaluate can do that. Evaluate. Now let's see. As far as I know, that evaluate can do. What? X, actually this evaluate function generates the value and then it is plotted. So I think that is the way to
So can simplify the function give that values?
no,
For
simplify will
example,
not. Simplify
simply
only
y
works for
of x
analytical solution.
analytic. Oh, okay. Okay.
uh,
So will you be sharing link of this recording uh, in today's session only or afterwards?
See, the problem, I mean, I already sent all the links. I mean, for the last 2 weeks videos link, I have sent it to the NPTEL. If now they are not sharing, then I have to share this link in the next class. Okay, so just remind me
Okay,
in the
sir.
next class, then I will just share. Okay.
Okay, okay, sir.
Mm, so y of 1 at this one is done by yes. Yeah, here you can do this, like writing y.1 the slash dot s. So this s is actually taking from this ndsolve and generating the value at 0.1. Now if we change the value to 0.5, it will give the value. Okay. Okay, so now if we use the table thing, that will t point s but t 0 to 10. I think this is the value most probably. I put this to 10. We can check here, like in 0 it is 1, then it is increasing slightly, then it is decreasing. So at 2 it is around 0.5 or something. So yeah, this is the value. So in this way you can generate the table.
Okay, okay. So thank you.
Yeah. Okay, so I will just now show the something that is related to the oscillator problem. This will take some time to type. I1. I'll just show it in the Mathematica desktop version. Can you see the desktop version?
Yes, sir.
Yeah. So this is basically the uh, command for the Lissajous figure. So here it is a superposition of two oscillation, that is the f of t a1 cos omega 1 t plus phi 1 and a2 cos omega 2 t plus phi 2. So ht is the superposition, and then I have plotted. Now if we do the parametric plot, then we will get this kind of figure. Now depending on the this sorry, depending on the amplitude and the phase and the frequency, the Lissajous figure's orientation will be changed. Like I have, if I put this one 1 and this one like escape by 4, then we cannot see any difference in the these oscillations, but actually if we do this, we can see the changes in the orientation. See, the Lissajous figure is already changed because the I have changed the frequency and the phase. Oh, sorry.
Sir, after that command, there is a semicolon. So, are we doing the shift enter again and again, even though semicolon is there, or it is changing automatically?
For these lines you are saying?
Yes.
No, I mean the okay. So here it is a semicolon. So you know the application of semicolon, right? It is suppressing the output. Like for example, if I use something like a equal to okay k equal to 5, sorry. So if I use enter, then it will go to the next line. If I use shift enter, then it will go to k equal to 5. Okay, but here if I use the semicolon, then now it is k equal to 5, but the output is suppressed. Now if I type k, it will show 5. Okay, now it depends upon, like I have used k equal to 6 colon, then normal enter, not shift enter, and then l equal to 7, then another colon, a semicolon, and then use the shift enter. Now previously I assigned the value 5 to value 5 to k. Now I have used 6. So see, I have used the shift enter and the value of k is 6. So using this semicolon, we are just suppressing the output, but it is the whole thing is running I mean all together. Like here you can see the input line is 44. So basically when here is showing a single line, input line is 44, then that means that the whole, all the commands are executing simultaneously. Okay. Okay, so now if I execute this one, the thing is the all this 1 2 3 4 5 6 7, the 7 lines of commands are executing one by one. Did you get it?
Yes, sir. Yes, understood.
Okay, so now this one is I think in the example or in the assignment, I could not remember properly, but this is the table for the prime numbers, that is the 2 3 5 7 and all those things. Now I have written the array again and enter, and then the find fit, so it will give the value of this particular function. Then uh, then again I have used this value of a, b and c in this particular line to produce the table using this value of this parameter, and then I got this one. So now here I can, what I can do, I can increase the number of prime numbers, then just copy it, paste it here, then again I will fit, the value should change a little bit. Yeah, it's changed. Now what I will do, I will just evaluate the value up to x10. So now it's changed a little bit. So according to this fit, the first value is 1.01713, which was supposed to be 2. Then for 3 it is giving 2.779, and so on. So this is the thing, and then next example. Okay. Okay, so this is it. Now I will show one demonstration. Yeah, this is another demonstration. In the last class I have shown the demonstration for normal oscillation, but here it is a 4 oscillator with damping. So now in this particular thing, if we, the equation is that mx double dash t, which is the basically the acceleration part, then the kxt, and then bx dash t. Now the why it is force oscillator, because in the right hand side that is not 0, here it is a continuous force, that is a cos omega t, that is continuously driving the oscillator. Now now you can see all the thing. So this is the equation. Basically the position of a mass m on a spring with spring constant k, damping coefficient b, and sinusoidal driver with amplitude a and frequency omega can be described by kxt plus bx dash t plus mx double dash t equal to a cos omega t. So now this is the plot for the displacement with respect to time. So this is the parameters: mass equal to 4, spring constant 3, damping 1, driving amplitude 3, driving frequency 2. Now what I will do, I will just first uh, reduce the amplitude to 0. Okay, the oscillation almost gone. Now the spring constant I am increasing. You can see the oscillation is increasing. Again I am increasing the damping factor, and you can see the oscillation is going to 0 quickly. Now I am just increasing the initial position. So in this way you can visualize the displacement for the problem of force oscillator with damping. Now this is the parametric plot xt and x dash t. So here you can also see the thing. Now if we go to the position and add the amplitude, so by changing the amplitude it is changing a little bit, but what will happen if we use Let's reduce the spin constant. Now I'll now here you can see that when the ratio of this mass and spring constant is almost 1 and the driving frequency is also 1, you can see that these oscillations are not reducing exactly. You can say this is kind of a resonating situation. Okay, so this is the thing, and here it is, we can increase the time and see that what is happening after some time. And this is the phase, the parametric plot for this particular situation. So basically if I turn the forcing function to 0, so it is like this. But now if I increase the amplitude, we can see that the nature of the parametric plot is changing. So in this way you can see and visualize the effect of the parameters on the force oscillator with damping. So this is a CDF file which can be downloaded from the Wolfram. Any question?
No, sir. No, thank you.
Okay, so I would like to ask for some recommendation or feedback for the thing, like what kind of things you want me to discuss in the next class.
Sure, sir.
So what kind of problems you want me to discuss in the next class?
It should be said here or in feedback, sir? Feedback form or here?
Here you can say here, no problem.
Okay. Actually, some videos are pending to watch. So right now, sir, I don't have any input from my side,
Oh,
especially
okay,
on for the assignments.
okay. So I'm trying to add some problems from the assignment or some similar problems from the assignment. So let's see in the next problem solving session I will try to add more problems, some physical
Or
problems.
can you speak a little more on the examination part? Because first time I'm going to give the examination of NPTEL. So
So
means
basically the problems will be related to the assignment, that I can say, but
okay,
what will be the exact nature I cannot say because I don't have any information. I am only assigned to demonstrate some
okay,
problem solving.
okay, sir.
Okay, okay, so thank you. I will just end today's session.
Okay, sir. Thank you. Thank you very much.